Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we are going to investigate MH370 and the underwater acoustics facilities in the Indian Ocean region. How did MH370 disappear into the Indian Ocean? How is it possible for an aircraft like a Boeing 777 to simply disappear? In the modern global glasshouse, surely someone must have tracked the aircraft. Questions have been raised regarding potential detection by the over-the-horizon radar, underwater acoustic systems, and military radar installations. A lot of questions and few answers. Independent aircraft investigations brings you the established facts. We provide traceability of all evidence to a source authority. We make a clear distinction between factual data and analytical interpretation. We operationalize ICAO Annex 13 by embedding investigative discipline directly into the production of each episode. This ensures factual material, analytical work, and narrative outputs all remain clearly distinguished, traceable, and compliant throughout the life cycle of an investigation. Aviation news is covered on daily airline news as it happens. This channel is reserved exclusively for in-depth investigations. If you find this analysis useful and want to see future independent investigations, subscribing to the channel helps ensure this work continues. You will find the script for each episode together with the illustrations used as a downloadable PDF on my website mh370search.com under the tab Archive. Subtitles are also available in 12 different languages for each episode. In the previous episode, we examined what data exists on MH370 and what has been made public and what has been withheld. In this episode, we will examine the underwater acoustic data and what that tells us about MH370. And Dr. Kadri of Cardiff University has written several papers examining the hydroacoustic data that was available at the time of the disappearance of MH370. The Comprehensive Nuclear Test Ban Treaty Organization, CTBTO, conducts underwater monitoring as part of its International Monitoring System, the IMS, using a global network of hydroacoustic stations to detect potential underwater nuclear explosions. And this system can also be used to detect other sounds. Low-frequency acoustic energy from underwater detonation propagates efficiently through the ocean's sound fixing and ranging SOFAR channel, a natural deep ocean sound waveguide created by pressure and temperature gradients, and is recorded by deep ocean hydrophone triplets, allowing events to be detected at intercontinental distances and located by time of arrival analysis across multiple stations. And Dr. Kadri used the CTBTO data to show that aircraft crashes in the Pacific, the Atlantic, and the Indian Ocean can all be detected. And detection is not always certain. It is probabilistic. It's not guaranteed. And it depends strongly on the geometry and the ambient noise. Data from 11 different stations has been investigated in the case of MH370. So underwater acoustic data from the CTBTO stations at Cape Lewin, Australia, and from Diego Garcia South Station were looked at, both before and after the point in time where MH370 is estimated to have run out of fuel on the 8th of March, just after 00 UTC, and the satellite system rebooted for a brief time between 001929 UTC and 001937 UTC. Underwater acoustic data from the Integrated Marine Observation System, IMOS stations at Perth Canyon and Scott Reef was also analysed. Finally, seismic data from Amsterdam Island was also considered. And 3 separate teams have looked at this data. A team at the Centre for Marine Science and Technology, the CMST at Curtin University in Australia, under Alec Duncan, looked at 8 hours of data between the 8th of March 00 and 08 UTC from Cape Lewin, Diego Garcia, Perth Canyon, and Scott Reef. The team at Los Alamos National Laboratory in the USA, Dr. Richard Stead, Dr. Ed Fenimore, and Dr. Tom Kunkel, looked at the data from Cape Lewin, Diego Garcia, and Amsterdam Island. And the team at Cardiff University studied the CTBTO data in the MH370 timeframe in March 2014, but they also studied the data between 2009 and 2022 for 9 other aircraft accidents with ocean crashes at known locations, and also for 1 submarine explosive implosion accident, the ARA San Juan, in 2017. Ocean Infinity discovered the wreck of ARA San Juan on the 17th of November 2018. And hydroacoustics can detect large ocean impacts, and multiple groups have examined the MH370 era data. However, no definitive impact signal can be attributed to MH370 and clearly identified as the source being from MH370. Acoustic signals from an aircraft ocean impact would primarily arise from the initial surface strike and subsequent structural breakup, with possible contributions from cavitation and pressure-related failure of sealed components, which may follow. And if debris remained coherent, then a smaller seafloor impact signal might also possibly be detected. Following initial impact and breakup, discrete acoustic events may occur from the pressure-induced collapse or rupture of sealed components such as oxygen cylinders, fire suppression bottles, hydraulic accumulators, and even inflated tires as the wreckage descends. An aircraft crash exhibits a distinct acoustic time signature compared with natural or anthropogenic sources. High-energy impacting objects such as meteorites or aircraft generate characteristic broadband pressure transients. Hydroacoustic sensors are routinely calibrated using controlled explosions, earthquakes, and volcanic eruptions, and comparative studies exist for the limited number of documented aircraft crashes and submarine explosions or implosions. In the MH370 timeframe, the vast majority of detections originated from the Antarctic and are likely to be ice cracking events, although seismic events are also sometimes detected from a seafloor ridge between Australia and the Antarctica. There was also a small earthquake off the south coast of Java in the Java Trench in the MH370 crash timeframe. There are several seismic surveys which were taking place from ships in the Indian Ocean, which were detected both at Cape Lewin and Diego Garcia. The signals arrive from distinct directions. They're coming from the sea, so they're either anthropogenic, so airgun surveys or something similar, or biogenic, whales, for example, or natural seismic, earthquakes, volcanoes, or indeed an aircraft crash. The underwater acoustic network includes 11 hydrophone stations that monitor for explosions in the ocean, but can also pick up other sounds, such as whale calls at great distances. Signal spectrums indicate a significant amount of noise in the 0 to 4 hertz band. The signals in this band appear to have a broadband frequency content which is typical of acoustic gravity waves, AGWs. Signals are therefore filtered for low frequencies below 5 hertz with a high-pass Butterworth infinite impulse response filter. And frequency bands between 5 hertz to 10 to 20 hertz to 40 hertz and to 60 hertz are all analyzed separately. The analysis of the recording signals from past aircraft incidents reveals 3 different types of acoustic signature. The first type is characterized by distinct and rapid signals following energetic impacts. The second type includes signals with a longer impact time, and they are typical where a ditching has been attempted. The third type involves signals with higher uncertainty around them due to multiple factors such as the large distances, crossing through land, and unknown modes of impact, nose first or main body impact or wings first. However, the pressure signatures radiating during a high energy impact were found to be observable even at a few thousand kilometers away. And the ARA San Juan submarine case is a good example for demonstrating that acoustic signals that radiate in water can couple to the elastic seabed when approaching shallow water, then travel large distances inland before returning to sea, where they can still be recorded at the hydrophones. The speed of sound in water varies between 1,430 meters a second to 1,570 meters per second. Curtin University determined the speed of sound events arrivals in the MH370 timeframe to be around 1,484 meters a second, and their particular signal of interest, which arrived at Cape Lewin at 1,486.20 meters per second, and Perth Canyon at 1,486.35 meters per second. Curtin University also found that the internal clock in the Perth Canyon sensor had drifted from GPS time by 25.8 seconds since deployment, and was once corrected, then aligned with the Cape Lewin time of arrival. The 013450 UTC arrival stands out as being the only signal over this time period that originated from a northwesterly direction on a bearing of 301.6 degrees true. If this signal had originated on the seventh arc, then the sound event would have occurred at 0051 UTC on the 8th of March, which is some 25 minutes after the latest time it is thought that MH370 could have hit the water, according to the ATSB. The results of the various analyses are as follows. Firstly, from Curtin University. There was one acoustic event of particular interest that was identified and occurred at a time that could potentially link it to MH370. And it appears to have been received on one of the IMOS recorders near Perth Canyon, the RCS station, and the CTBTO hydroacoustic station at Cape Lewin, the HA01 station. The most likely explanation of the signals received at HA01 and RCS is that they are from the same acoustic event, but the source of the signal is unrelated to MH370. The characteristics of the signal are not unusual, and it is only their arrival time and to some extent the direction from which they came that make them of interest. It is also possible that this was a natural event and unrelated to the aircraft. The conclusion from Curtin University was the source of the event originated in the Chagos-Laccadive Ridge, which is a seismically active volcanic ridge stretching south from India toward Diego Garcia. It is also possible that there was a signal recorded at Scott Reef on the IMOS station at 013249 UTC, and that is recording the same event as the arrivals at HA01 and Rottnest, RCS. These share enough of the same characteristics that it's plausible that they're from the same event. And if that is the case, then we have a triangulation to an area which is geologically active Carlsberg Ridge, southwest of India. Los Alamos National Laboratory said that there were only 3 potentially applicable stations where signals of interest could be identified. That's HO1, HO8, and AIS. HO1 is Cape Lewin, HO8 is Diego Garcia South, and AIS is the Geoscope station on Amsterdam Island. And of these 3 stations, only HO1 has a very interesting and potentially applicable arrival. HO8 is contaminated by a long series of large amplitude repeating and interfering signals that completely obscure any possible applicable arrival. And AIS is also contaminated by natural noise sources and has a sample rate which is sufficiently low as to likely exclude any signals of interest. And Cardiff University conclude that there's a practical suggestion to help resolve the ongoing debate regarding the detectability of acoustic signals radiated by MH370, and that is to conduct controlled explosions along the 7th arc. similar to the explosion that happened with ARA San Juan, the submarine. And these explosions should contain an equivalent amount of energy believed to be associated with the crash of MH370. If the received signals from these explosions exhibit comparable pressure amplitudes to that of the signals of interest, that would support the notion that the identified signal should be a focal point in future search efforts. And conversely, if the signals received both at H01 and H08 are significantly stronger than the signal of interest discussed here, it would necessitate further analysis of the signals from both stations. Now, there are two important points we need to discuss. Firstly, sounds can be weakened by reflection and absorption in the ocean. Whenever sound reflects from the rough ocean surface or seafloor, some sound energy is scattered and lost. A sound wave that hits the ocean surface or seafloor many times will be too weak to be detected. Sound that does not hit the ocean surface or seafloor will still lose energy due to absorption. Low-frequency sounds lose very little energy, however, due to absorption. The result is that low-frequency sounds that do not interact with the ocean surface or sea floor can be detected after traveling very long distances through the ocean. The amount of absorption increases as the frequency of the sound increases, and higher frequency sounds are therefore only detectable at short distances. The distances at which sounds can be detected depends on the frequency and, of course, how loud the source is and how loud the background or ambient noise is. And the second important point is that sound do not follow a straight line path in the ocean. Sound waves traveling in the sound channel follow many different paths. When the sound source and receiver are located at the depth of the sound speed minimum, called the SOFAR or sound channel axis, sound waves travel nearly straight down to the axis and cycle above and below the axis, almost reaching both the surface and the bottom. Although sound travels away from a sound source in all directions, of course, only sound traveling away from a source on a path that leads to a specific angle towards a sensor is important. The sound waves traveling on these different paths have different times of arrival, and a single explosive source will therefore be heard as a number of separate arrivals leading to the characteristic signature of a SOFAR transmission building up to a climax. And sound paths from a source near the surface come together or converge, creating regions of higher sound pressure at about the same depth as the source, every 50 to 60 kilometers away from it. And these regions of higher sound pressure are called convergence zones. In between the convergence zones, there are regions of lower sound pressure, and these are called shadow zones. So, in summary, no definitive impact signal attributable to MH370 was identified. The various studies broadly align with signals of interest in the MH370 timeframe, but conclude the source was either an ice event from Antarctica or a natural or man-made seismic event, and not from MH370. Either the direction of arrival or the timing of arrival of the acoustic event did not fit the Inmarsat satellite data or the Boeing fuel range or the Cicero or UWA drift analyses. My co-author, Professor Simon Maskell, was the scientific advisor to Ocean Infinity for the recently proposed underwater search for MH370, which was originally planned in November 2024 and conducted intermittently in early 2025 and again in early 2026. He had a member of his team looking at the CTBTO data, and he reports it doesn't look like there's any positive evidence of the sensors having a confirmed detection or having heard, in inverted commas, the aircraft hitting the sea. However, he thinks we can use the negative information to help localize the search area. And he has someone using models for acoustic propagation through the ocean, assessing whether there is anything useful we can extract from the data and from the lack of data. In the next episode, on the 20th of February, we will present a plausible hypothesis as to what happened to MH370 that fits all the data presented in the previous 6 episodes. We will bring an integrated end-of-flight reconstruction that reconciles independent datasets, including the Boeing end-of-flight simulations, the DSTG and Inmarsat BFO analysis, the Inmarsat's satellite timing, the whisper propagation geometry, the fuel exhaustion constraints, the floating debris damage assessments and drift analysis, the hydroacoustic recordings from CTBTO, IMOS, Lanel, Curtin, and Cardiff universities, the Southern Indian Ocean meteorology, and human factors timing considerations. The objective is not to assert intent, but to identify a physically and temporally coherent terminal sequence consistent with all available technical evidence. Please leave any comments or questions that you may have. We will address the key points in the next episode and publish responses on YouTube and on our website, www.mh370search.com. Thank you very much for watching, and please subscribe for future investigations.